So we're looking at changes in entropy. Is the entropy going up or is the entropy going down? And so we could look at it qualitatively first. Qualitatively here, if we go from solid to liquid, does the entropy go up or entropy go down? Up, yeah. Liquid is more disordered, less constrained. Solid is more ordered, more constrained. So entropy goes up. So delta S increases greater than 0. If we go liquid to gas, entropy's gone up. Liquid should have a lower entropy. The molecules should be touching or attracted, whereas gas is going to have a higher entropy, a lot less constrained, a lot more disordered. Solute and solvent goes to solution. Well, here we have the solute separated from the solvent, and so this looks more ordered. Here, this looks more disordered. And so it looks like when we dissolve things, the entropy goes up. And so qualitatively, it's not so bad, but we can't leave it at qualitative. We have to figure it out quantitatively because we have to compare it with the energy change. And so how do we determine the change in entropy quantitatively? Well, I'm just going to cut right to the point. The way we determine entropy changes is we just look at the final entropy minus the initial entropy. That's it. So the final entropy minus the initial entropy. Well, where do we get these? These are called the absolute entropies. So we just look at the difference in absolute entropy. The absolute entropies are found in Appendix D. So when we look in Appendix D, we see delta H of formations, which we use, Chem 1A. We see delta G, which we're going to use in Chem 1B, so ignore second column. It's the third column here. The third column is S, the absolute entropy. And so here, do you know what that little superscript means? S naught, or S superscript 0? It means standard thermodynamic conditions. Standard thermodynamic conditions refers to what? Zero Celsius? Actually, no. There's no standard thermodynamic temperature. There's only a standard thermodynamic pressure and a standard thermodynamic concentration. Pressures are going to be 1 atmosphere, 1 bar. Concentrations are going to be 1 molar. The pressure can be anything, and we could still be under standard conditions. It just so happens this data table is for 298 Kelvin. Now, looking at these numbers, the first thing we come across is something like this. 2833 minus 321.7, 110.7490. So we got the numbers here, and we can use them. But you don't want to use these numbers blindly because we want to know something about these numbers. And so something about these numbers, let's take a look here. Like this. Now this is the Boltzmann equation. And so Boltzmann came up with this equation saying that the absolute entropy is equal to K. This is not the rate constant, this is a Boltzmann constant. Boltzmann constant is just R per molecule rather than R per mole of molecules. Ln, natural log of W. W is the number of ways to arrange things. And so, for example, if there's only one way to arrange things, and then that's highly ordered and constrained. And so this beaker, there's many ways we can arrange it, even in one position. But let's say this label has to be pointed at this angle or whatever, then there's only one way to arrange this, right, on the shelf. And so if we only have one way to arrange things, then everything's perfectly ordered. You know, everything's in its proper place. So if W is equal to 1, there's one way of arranging everything. Then the natural log of 1 is 0. And that means the entropy is 0, the absolute entropy. And so using the Boltzmann equation here is this. If everything's perfectly ordered and there's only one way of arranging it, then the entropy should be 0. And so here, W is the microstates, but we can back up. Here, this is starting to get into theory. A lot of the stuff with entropy didn't come from theory. Do you know where the laws of thermodynamics came from? Did they come from theory or did they come from experiment? Experiment. And so the laws of thermodynamics were developed hundreds of years ago before atoms and molecules were widely accepted. So you don't even have to believe in atoms or molecules to get this. Now we're starting to get into theory with these microstates and other stuff. So, but back then, but you know, these laws are special because if you think about the ideal gas law, are there exceptions to the ideal gas law? Are there cases where the ideal gas law just doesn't work? Yeah. Are there exceptions to the laws of thermodynamics? You would think so. You know, like any other law, there's going to be exceptions to the law. But, you know, people have been trying for hundreds of years to find one single exception, one single failed calculation in thermodynamics, but they haven't. And so, yeah, this law is at a different standard. Well, in terms of microstates, this is what we see here. You know, there are fewer ways of arranging things because there are only two energy levels. This is a Boltzmann. What we're looking at here is a Boltzmann thermal distribution. Do you remember the Boltzmann thermal distribution, the Maxwell-Boltzmann thermal distribution, where we plot population versus kinetic energy? Let's just do energy. And we get a curve like this, right? And so what we're going to do is we're going to take this curve and tilt it on its side like this, and then flip it around. And so what we're doing here is we're looking at the Boltzmann distribution curve like this, in which the high energy tail is going to go up. And so the bulk of the population will have this energy here. And then as we get higher and higher in energy, the population decreases. And so that's what we see. And so this is a fixed temperature. And so the distribution is kind of the same for all these. Oops. Etc. And so you can see how the population distributes itself between the energy levels. Here. If we increase the temperature, what that's going to do is it's going to flatten it out. So the lower energy population decreases and the higher energy population increases. And so it's just a Boltzmann distribution, thermal distribution, arranged vertically rather than horizontally, shown over there. But what we can see is we can see differences in microstates. And the more microstates we have and the more distributed, the higher the entropy is. This isn't Boltzmann equation, but it just shows that the entropy is related to heat. This is Q is heat, and ReV stands for reversible, divided by temperature. And so when we're looking at entropy changes, you know, it also depends on the heat transferred there. And so what types of things have a lot of heat transfer? One of the things that has a lot of heat transfer is something like water. You know, water has a pretty high specific heat. Water has a pretty high heat of vaporization. Water has a pretty high heat of fusion or heat of melting. And water's high specific heat is due to it can absorb a lot of energy and the temperature doesn't go up much. And so water can absorb a lot of energy. That means there are a lot of different ways to distribute that energy in the water sample. It can cause rotations, vibrations, translations, etc. And so that means it has a relatively high entropy. But let's go back to Appendix D. According to the Boltzmann's equation, the lowest entropy we can have is when there's only one way of arranging things. When you start to get to more and more ways of arranging things, the entropy starts to get higher and higher. And so if there's only one way of arranging things, then the lowest possible entropy we can have is 0. And so is this a typo? Minus 321.7. What do you think? Is that a typo? It turns out there are other negative numbers in here, and therefore it's not likely a typo. Well, how can we have a negative entropy? Does that mean there's something even more perfect than perfect? Because if everything's perfectly arranged and there's only one way of arranging it, then entropy is 0. And so there's something strange going on here, but it depends on how familiar you are with Appendix D. How familiar are you with Appendix D? Do you understand Appendix D? Appendix D is not easy to understand. Do you guys understand Appendix D? Do you know the other strange? From Chem 1A, there was another strange thing that happened. Do you recall what that strange thing was? Do you remember this from Chem 1A? There's about a paragraph in Chapter 7 written about this. But that is this. The delta H of formation, the standard enthalpy of formation for H2 gas is 0. Well, that's what we expect, because this is a formation of H2 gas from H2 gas at 298 Kelvin. There's no difference. H2 gas going to H2 gas should involve 0 energy change. But the strange thing was with this. The standard enthalpy of formation for H plus is 0. And that's actually very odd, because this is forming H plus, 1 mole of H plus, from the elements in the standard state. So element is hydrogen, H2 gas, and would need half a mole of this. And so this delta H is equal to 0. How can that be 0? Because if we have a half mole of hydrogen, we got to break those bonds first. Break a hydrogen-hydrogen bond is going to cost you like 400 kilojoules of energy per mole. So this half a mole is going to cost you about 200 kilojoules of energy. And then we have to ionize this. Do you remember the ionization energy for hydrogen? Ionization energy for hydrogen is over 1,000 kilojoules per mole. It's more like 1,300 kilojoules per mole. So we're talking about 1,500 kilojoules per mole to break the bond and to ionize it. Then we get some energy in return by hydration or solvation. You learn about hydration and solvation in chapter 13. And so, is this really going to result in 0 energy change? What do you think? It costs 0 energy to interconvert hydrogen to H plus and H plus to hydrogen? No. And so this is the first strange thing that happened. This happened in Chem 1A in this chart. These don't make sense. Well, this one makes sense, but this doesn't make sense. And so how is that explained? How could this be 0? In fact, in Chem 1B, we carry this on, this strangeness on further. What is the absolute entropy of H plus AQ? H plus AQ has an entropy of 0. Does that mean H plus AQ is perfectly ordered? There's only one way of arranging all the H pluses and all the water molecules? No. Absolutely not. And do you think they're related? Do you think these two strange entries are related? Yes, they are. They're related. They have the exact same reason. And what was the reason from Chem 1A? Yeah, it was arbitrarily chosen to be 0. How come? How come it was arbitrarily chosen to be 0?
We can measure the directly. We can just measure
Yeah, this is good. That's good memory. This is good memory. And so basically it had to do with this guy, HClAq. HClAq, this is what was discussed in the chapter. Delta H of formation of HClAq here is minus 162 kilojoules per mole of HClAq. And the reaction here is we're going to take the element 1/2 H2 gas plus 1/2 Cl2 gas and react those. Well, HClAq is a strong electrolyte, so HClAq consists of H plus AQ plus Cl minus AQ. And so what we have here is the delta H for this is equal to the delta H of formation of H plus the delta H of formation of Cl minus. So that 167 kilojoules is equal to what it takes to form the H plus and what it takes to form the Cl minus. But we have two unknowns here. Two unknowns and one equation. If we have two unknowns and one equation, then we need a second equation. But there is no second equation. If there's no second equation, you have two choices. One, you say the problem is impossible to solve. Or two, you make an assumption. And so the assumption that they make is that, well, it's not really an assumption. They're just going to define this as 0. So delta H of formation for H plus is defined as 0 kilojoules. It isn't really 0 kilojoules, but you know, that's as good as any choice because you can't say it's 50-50. Half the energy is for H plus, the other half for chloride. Can't be that either. And so might as well pick something easy. And so you pick something easy, but you're going, that's way off. You know, that's impossible. But here is the reason why we can do it. The reason why we can do it is this. Can you form a cation without forming an anion? If you form a cation, you better form an anion too, otherwise we aren't conserving electrons. You can't create or destroy those. And so all the cations are going to be systematically off. All the cations are referenced to delta H of formation of H plus being 0. And so all the cations are off one way, and all the anions are off the opposite way, equal and opposite. And so what happens is, okay, the anion is going to be off, and so delta H of formation for the anion, chloride, is going to be minus 167. And so that's way off, because that's not really the amount of energy. But when you add the two, this one has an error one way, this one has the error in the opposite way, and when you add the two, the errors cancel each other out. And so since the errors cancel each other out, then that's okay. We can go ahead and arbitrarily set this to 0. Now, that means there are actually 3 tables in one. There's the cation table, the anion table, and the neutrals. Neutrals being elements and compounds. And so the trick is this. Let's say you had a table that just lists the numbers. And these numbers could be the Celsius, the Fahrenheit, or the Kelvin temperature. And so you see 2 numbers in the table, and you go, okay, which one's a higher temperature? Minus 10 or plus 10? Which one's a higher temperature? You'd say plus 10 is a higher temperature. But then I'd say, no, you're wrong, because I meant plus 10 Kelvin minus 10 Celsius. Well, minus 10 Celsius is a much higher temperature than plus 10 Kelvin, and so you're wrong. Well, then you would say, that's not fair, because you didn't tell me the units. right? If you knew the units, then it would have been an easy question to answer. Well, this is not fair. This is not fair because they aren't telling you. You can't compare. This is like having the Celsius, the Fahrenheit, and the Kelvin temperature all together. All the numbers are here, but there's no units. They say, well, no, it's fair because you should know. But when I asked how many of you knew, no, you know, maybe one person knew, right? And so this is why this is not a fair comparison. So this is a question I ask all the time. Which one has a higher entropy? 28.33 or minus 321.7? Which one has a higher entropy? Well, you know what most people say on the multiple choice? They say 28.33 has a higher entropy. But then I say, no, that's wrong. Minus 321.7 is a higher entropy. And then you say, what? Because, why? It's not a fair comparison. This is like 28.33. Kelvin versus minus 321.7 Fahrenheit. And then, yeah, minus 321.7 should be a higher temperature because it's minus 450. 4 is around 0 Kelvin. So, you know, it's not fair. So you have to be aware of that. And the answer is, well, you should know. You're supposed to know this. You know, this is a cation, right? Cations are an arbitrary reference. And so the same thing here. There's going to be entropy change. Now, how do we figure out what the entropy change is? You know, how were these entropies determined? These entropies, do you know how they're determined? Are they determined using the Boltzmann equation? No, it turns out they aren't. Because there are too many microstates you have to total. The entropies are determined experimentally. And so how do you determine the entropies experimentally? You do it like this. We use a little bit of calculus. ds is equal to the integral of dq over t. dq is what we call the heat capacity, Cp over T, heat capacity at constant pressure, etc. Delta S or ds, delta S is just S final minus S initial. And then we have something called the third law of thermodynamics. The third law of thermodynamics says this. Third law of thermodynamics says that the entropy of a perfect crystal at 0 Kelvin is 0. So we have our initial temperature at 0 Kelvin. This is just the integral. Integral was something in calculus, but integral is basically the area under a curve. And so the way this is going to work is we do some calculus. And this stuff you don't need to know. But you measure heat capacities at different temperatures. The heat capacity measurements can go very low, to 4 Kelvin. And so let's look at water as an example. Here, the heat capacity of liquid water is fairly high. And so it jumps up. And so we have solid here, and then we go to liquid here. Liquid water has a much higher heat capacity than solid. And then we go to gaseous water, H2O gas. H2O gas, the heat capacity drops down again. And so this is the heat capacity curve. So the heat capacity curve we can measure, you know, we can extrapolate this out. Jump up here, jump down. And then from the calculus, what you do is you determine the area under the curve. So let's say I want the entropy of ice at this temperature. If I want the entropy of ice at this temperature, I'm going to integrate or determine the area under the curve from 0 Kelvin to this temperature. And that would be the absolute entropy at this temperature. If I want the absolute entropy of water at this temperature, I'd just continue. And so the area under that curve would be it. If I want the area of steam at this temperature, I just continue. The area, and so this would be the steam. So basically, once I figure out the areas, then I can plot out the entropies versus temperature. And so you can see the entropy of solid, this is methane, no wonder. I thought this was water. See, I have it, water. We'll just go with methane. That's the same thing. I can measure the heat of it. So the entropies, these would be the absolute entropies. You can see a jump here in the entropy for the liquid and another jump for the gas. This is gaseous methane here. And so we can determine the entropy at any point, that is at any temperature. And so here we can get it. Well, Appendix D is only going to do one temperature. And the one temperature is going to be 298 Kelvin, i.e. room temperature. So methane's a gas at room temperature. That would be the entropy, and that would be listed in Appendix D. However, we have a lot more entropy data here that's not listed in Appendix D. And it's just an overwhelming amount of data, so therefore we're just going to limit the data in Appendix D to 298 Kelvin. All right, this is the third law of thermodynamics. So once we get all that, then we compile all this data in Appendix D, and what we want to do is we just want to use it. So then our quantitative entropy calculation is very simple. All we do is we take the entropy of the final minus the entropy of the initial. And so let's go ahead and do one really quick entropy calculation here. We saw that going from H2O liquid to H2O gas involves an increase in entropy. So H2O liquid goes to H2O gas. Delta S for this should increase. That is, delta S is greater than 0. Entropy increases. Now, we want to put a number on this. And so, to put a number, we need the entropy of H2O gas. We have 1 mole of that. The entropy is going to depend on how many moles you have, because the more moles you have, the more positions you can arrange things in. Minus the entropy of H2O liquid. Okay, this is going to be at 298 Kelvin. And under standard conditions. And so all we do here is we just look it up, the values. So the entropy of H2O gas is 188.8. The entropy of H2O liquid is 6991. So this is 188.8 joules per mole Kelvin. We have 1 mole, so the moles will cancel out, just joules per Kelvin. Minus 69.91 joules per mole Kelvin. The moles cancel out because we're only dealing with 1 mole. And so that tells us quantitatively what the entropy change is. Very simple, right? Entropy calculation. Entropy calculation is very simple. We have Appendix D. We can use Appendix D to figure it out. Now, what we should do is we should take a look at the numbers. You know, what's the lowest entropy we have? Well, is the lowest entropy we have the minus? No. The minus are deceptive, right? Because that's an arbitrary 0. And so let's take a look at some of the lowest entropies we have and the highest entropies we have. So if I start scanning through, I'll find the lowest entropy looks to be here. Take a look. This is close to 0. Diamond. The entropy of diamond is 2.38. Only the lowest entropy on the table. What's the highest entropy? The highest entropy are a few hundred for the neutral species. And so what we see here is this. You know, the pattern is like the, although these are off slightly, but the pattern is solids typically have entropies between 0 and 100. Some solids are unusually disordered. Like, for example, calcium phosphate. Now, calcium phosphate has an entropy of 236. That's because there are lots of ways of arranging the phosphates in there, in the crystal structure. But most solids are going to be between 0 and 100. Most liquids are going to be between 100 and 200. But some liquids are going to be lower, like water. Water is a little bit better ordered. And some liquids are going to be higher. And then gases are going to be over 200. And some gases are lower, some gases are higher. For example, steam is lower. Some of the other gases are higher. It has to do with how well ordered or disordered they are. All right, I'll stop here. This is where